This episode, starting off promisingly enough like a fairy tale about the snake, the bird, and the dolphin, will take an unexpected twist to discuss the graphs of rational functions instead. Very quickly, rational functions are numbers that can be expressed as fractions of two integers, in which case the denominator is non-zero. In simple English, we are looking at graphs where the powers of x can be expressed as such fractions. Simple examples include the x squared graph, as the power of 2 can be expressed as 2 over 1 for a quadratic curve. The power of negative 1 can also be expressed as negative 1 over 1 for a common looking graph like this. But those are simple cases. The good news is that there is only one problem for graphs of rational functions. The bad news is encompassing though. It's just awfully difficult. You have your usual parabola. You also have a discontinuous curve like that, and another one shaped like a volcano, a curve that's in the first and third quadrant, another V-shaped curve, and another S-shaped curve lying down. How are you going to sort through this mess? We start off by analyzing the fraction in a 2x2 grid. There are only two options for a numerator p and denominator q, namely, they are either odd or even. I've listed some examples in the grids, but before we proceed, hang on a moment. Do you realize that fractions whose numerator and denominator are both even can always be simplified? And when you do so, these fractions inadvertently fall back into one of the three grids. Great news for us then, as it means that there are only three cases to fuss over. Let's start with odd values for both p and q. The first possibility is if p is larger than q. Examples of such fractions include 3 over 1, 5 over 1, and 7 over 3. Observe that the shapes of this curve resemble a snaking pattern through the first and third quadrants. These y values increase at a decreasing rate to an inflection point, then increase at an increasing rate. In fact, here are more examples of such curves. But what if the p value is smaller than q in a fraction? Fractions such as 1 over 5 and 3 over 7 for example. In these cases, note how the curve solely exists in the first and third quadrant, but the y values form a snaking pattern sideways instead. Once again, more similar examples to show the snaking nature sideways. For now, we have locked in two observations. Number 1, fractions with both odd values in their numerator and denominator can be generalized as a snake form. And 2, that the curving nature up or sideways depends on the magnitude of these values. Now, on to our second case. What if the fraction has an even value numerator and odd value denominator? And also, that the p value exceeds that of q. You can plot the points, but long story short, all resemble U-shaped graphs, much like a bird with its wings pointed up. Once again, a few more examples here, and they all reside neatly in the first two quadrants. If you spot a pattern by now, it should be no surprise that I'll be investigating an even numerator value which is smaller than a large odd denominator value. The nature of these fractional indices yield y values that increase slowly, resulting in curves shaped like a bird with its wings out sideways. A few more case studies here all show the same general outcome. So now, adding on to our knowledge bank, even numerators with odd denominators are all bird-shaped. Our last case here has to be a fraction with an odd numerator and an even denominator value. With a large numerator value as a power, y values have to increase quickly and they will look like a dolphin plunging straight out of the water. Observe how these other similar curves reside only in the first quadrant with the same curvature and realize that this isn't so difficult after all. And with that, the last case will be straightforward. As you may have predicted, a small odd numerator and large even denominator will form graphs which resemble a dolphin reaching to the side. And once again, only in the first quadrant. To summarize what we know, graphs of rational numbers expressed as odd numerators and even denominators will resemble a breaching dolphin in the first quadrant. Can we roll the credits yet? Hang on, there's still one aspect that we have left out. What is the impact when the power is a negative rational value? A mnemonic would help in a case like this. NEGATIVE stands for never ever getting anywhere to intercepts or vertices ever. I'll show you how it works here. This is an x-cubed graph residing in the first and third quadrant. So, the x to the power of minus 3 graph will reside in these quadrants too, but without touching the axis and with no turning point. Likewise for the x to the power 1/3 versus x to the power negative 1/3 default graphs. If x to the power 4 curve lies in the top two quadrants, x to the power of negative 4 would as well as discontinuous curves. The same applies for the other bird-like curve too. As for the Dolphinesque curves, the negative counterparts only exist in the first quadrant without touching the axis. Rounding up, the snake, bird, and dolphin are three animals that best represent general shapes of three types of rational numbers. Comparing the numerator versus denominator helps you plot which way the curve is heading, and the negative power automatically causes the curve to deviate from both axes.